key component here is coupling nitrification and denitrification to convert the forms of ammonium and nitrate to nitrogen gas N2, which is an inert gas and is not harmful to the environment and can just join the natural nitrogen cycle once again, so that nitrogen is not lingering in the environment and causing issues like eutrophication. And these systems remove 50 to 75% total nitrogen. So that being said, we have some things to consider when we're talking about OWTS in Rhode Island. So first off, effluent nitrogen concentrations are not monitored after the initial installation of the systems, and that combined with the possibility that installation and maintenance may affect system performance leads to some uncertainty surrounding the performance of these systems, and that led us to our hypothesis that the inputs of nitrogen to coastal systems could possibly be higher than expected because, again, we're not sure what's coming out of the systems in terms of nitrogen. So our approach to solving this issue is to first monitor system performance of existing systems in Rhode Island and develop a model that will help us understand how we can tweak the systems to make them better at removing nitrogen and adjust the underperforming systems accordingly, and then measure changes in response to adjustments and continue to monitor all of the systems. So for our sampling design, we have a total of 42 systems that we sample each month. 17 are AX20 systems made by Arenco, 14 are FAST systems made by Biomicrobics, and 11 are Septic D systems. And then for our site locations, we have 6 different towns that we sample from, and all are located within the greater Narragansett Bay watershed in southern Rhode Island. So in order to keep track of the performance of these systems, we have a variety of operational parameters that we measure. Some are measured exclusively in the field, and others are measured just in the lab. And then we have this middle portion here that are measured both in the field and in the lab. And this has proven to be a really helpful part of our project because it allows us to analyze the accuracy of the field analyses because we have lab values for those constituents. So that brings me to my first point of the talk here, which is the evaluation of the rapid field tests. So we know that rapid field tests are used by O&M service providers to evaluate system performance. And these field tests are things like test strips. So you would dip those into a sample and wait a certain amount of time, and the test pad would change a certain color according to the concentration of the constituent. And also test kits, which use similar colorimetric methods, just having liquid reagents. And these are quick, and they provide results on site, so eliminating the need to go back to the laboratory, and so that we can make evaluations about the system performance on site, and they're also inexpensive. So we really wanted to figure out if these provide accurate results and also provide field tests that are accurate, that we can rely on. So to do this analysis, we went out in the field and took samples from our 42 systems, and we performed a rapid field test on those samples out in the field. And we took the samples back to the laboratory, and we performed a standard laboratory method on those, and then we compared results from the rapid field test to results of the standard laboratory methods. And we needed to come up with a concrete definition of accuracy in this case. So we used a linear regression model. So we plotted the laboratory values on the x-axis and the rapid field test values on the y. So if we got a laboratory value of 1, our rapid field test should give us a value of 1 as well if it is accurate based on the lab value. Same with if we got a lab value of 3, we should get a rapid field test value of 3. And if we kept going with this, we would get a linear function with a slope of 1 and an intercept of 0. So we went in and did one of these graphs for every single field test, And then we statistically analyzed to see if the line that it yielded was statistically significantly different from a line with a slope of 1 and an intercept of 0. And if it was statistically different from a line with a slope of 1 and an intercept of 0, it was considered to be inaccurate. So we used test strips for alkalinity, nitrate, ammonium, and pH out in the field, and we found that all of them were actually inaccurate. We also used a dissolved oxygen titration kit, and that was found to be inaccurate as well. And we used this pH pocket meter, which was actually found to be accurate. So when we look at this in terms of statistics, we can see that all of the methods that were inaccurate have either a slope or an intercept that was different from that one-to-one line, and the asterisk represents a statistical difference. And then the pH pen was accurate, so we don't see any asterisks, and therefore the line that it yielded was not statistically different from the one-to-one line. So we were suspicious that the field conditions would introduce error, and we thought that was part of the reason why all of these test strips were inaccurate out in the field. So we actually took samples inside and completed the test indoors, and when we did that, we found that the accuracy actually increased, and all of the test strip methods were found to be accurate based on that linear regression model. So when we look at it statistically, we can see that none of the test strips, when they were tested inside, had intercepts or slopes different from the one-to-one line. So when we took out field conditions, we actually increased the accuracy of these field tests. So we think that out in the field, the differing light conditions can introduce error, and we already have a very subjective process that we're relying on to decipher between different colors on that color chart to determine the concentration of the constituent. So we think that the differing lighting conditions during the day and different times of the year can actually add to this issue. So varying light conditions can actually complicate that visual comparison that you're making to the color chart. So again, if we use them inside, we can actually increase their accuracy. So we wanted to provide some accurate rapid field test methods that we could actually use in the field and rely on them for accurate results. And we went out and tested some other brands of test strips. So we tested these 5-in-1 test strips by API. They test for pH and nitrate on the same test strip, and those were found to be accurate when used out in the field. And also this ammonium test kit was found to be accurate. And then we're currently testing this photometer that's made by Hanna Instruments, and it can test for ammonium, nitrate, and COD out in the field. So now I'm going to go over the evaluation of the performance of OWTS. So for this analysis, we used final effluent total N concentrations, and they were collected from March 2015 to May 2016. And we reported standard laboratory values. And I want to point out here that when we first started the project, we only had 4 systems out of the 11 Septic systems that were actually turned on for that denitrification mode. So in the first graphs I show you, I took out those systems that weren't turned on for denite mode because it was unfair to represent them. But then I also have some other graphs showing those that were not originally turned on and then their performance since they have been turned on. So to date, they actually have all been turned on. So this first graph here is the distribution of total N concentrations from March 2015 to May 2016. So this is every single sample point we have for every single system, but it's divided up by system type. So we have the system type on the x-axis and total N in milligrams per liter on the y. And to just go over the elements of the box and whisker, the median is the middle bar here, and the 10th percentile is this bottom bar, the 90th is the top, and then we have the 75th and 25th percentiles, and every out-of-range value is represented by each dot. So we can see right away that the median total N concentrations for all system types are below the 19 milligrams per liter standard, so that's a good thing. And we can also get an idea of how consistently these systems perform. So looking at how compressed the box and whisker plots are will tell you how consistent of a performer each system type is. So based off of that, it looks like the Septic are the most consistent performers, followed by the Advantex and the Fast, which have a pretty large range of values. And I also wanted to point out that there are some really low values, so we know that these systems are capable of removing a lot of nitrogen, and that gives us a lot of hope when we try to adjust them and make them better at what they do. So this next graph shows all of the individual Advantex systems for the same sampling period. So we have the individual AX systems on the x-axis and total N in milligrams per liter on the y, and then that dashed line is the 19 milligrams per liter total N standard. So if we break this up into systems that are performing to standard, which means that they have a median total N concentration of 19 milligrams per liter or lower, we can see that 71% of the Advantex systems meet that standard. This graph is oriented the same way, except it's showing just the individual fast systems. And when we break that up into systems that are performing to standard and those that are not, we get 57% of fast systems are meeting the standard. So this graph is for the Septic systems, and again, I only included the individual systems that were turned on for D-night mode from the beginning of the project, and 50% of these systems meet the total N standard. So now I have a graph showing you all of the individual systems that were not originally turned on for D-night mode. So this graph on the left is from March 2015 to December 2015. And we can see that 14% of the systems meet the 19 milligrams per liter standard. And then I'm going to show you this graph on the right, which shows the performance of the systems since they were actually turned on. So we made a switch, or the service providers made that switch in January. And so we can see that since they were turned on for the D-night mode, so more nitrified effluent is returned back to the headworks of the system to be denitrified. We don't see much of a change in the performance since they were actually turned on for that denitrification mode. So we wanted to compare our results to results of a similar study that was conducted in Barnstable County, which is made up of 15 different towns on Cape Cod. So this graph shows the median total N concentration of Narragansett versus Barnstable County systems. So we have system type on the x-axis and total N on the y, and again that dashed line represents the 19 milligrams per liter standard. So we can see that for all three system types, the median total N concentration is higher in the Narragansett systems than the Barnstable County systems. And also I wanted to point out that this analysis includes the systems that aren't turned on for denitrification mode, just because I couldn't extract the ones that were not turned on for denitrification mode in the Barnstable County data set. So I just wanted to include the ones in our set to make it a fair comparison. So the AX and the FAST systems for both Narragansett and Barnstable County systems are below the 19 milligrams per liter standard, but the Septic are the only ones that have the median total N concentration above 19. But again, those include the ones that were not turned on for D-night mode. So this graph is showing the percentage of systems that are in compliance between the two states. It's oriented the same way, except their percentage of systems in compliance is on the y-axis. So again, it follows the same trend. So there's a higher percentage of systems in compliance in Barnstable County for all 3 system types. And again, it includes the systems not turned on for D-night mode. So we think that this difference in performance between the 2 states is likely because of differences in regulations between the 2 states. And we think it's a fair comparison to make because the 2 states have similar geologies and climates. So in Rhode Island, we have 2 maintenance visits that are required per year, but these maintenance visits are really focused on mechanical function, and so they do not include effluent sampling. But we do have the 19 milligrams per liter standard. In Barnstable County, Massachusetts, there are 4 maintenance visits required per year, and effluent sampling is required during these visits. And there's also that 19 milligrams per liter standard. So one thing that Barnstable County has that Rhode Island lacks is this online management database system, and that actually allows for maintenance visits to be tracked and effluent constituent levels to be tracked as well, and it can send alerts when effluent does not meet the standards. Oops. So we think that the effluent sampling required and the additional maintenance visits, as well as that online management database system, really allows the O&M service providers to get a better understanding of what's going on in their systems, and it leads to more proactive site visits. So if they know what is coming out of the systems in terms of nitrogen, they can then make system adjustments and also keep revisiting the systems until they are performing to standard. Okay, so now I'm going to go over the predictors of effluent total N. And to orient you as to where this coincides with our project, this part goes along with the development of the statistical model for performance optimization. So understanding how we can adjust the systems in order to get them better at what they do. So in order to answer the question, which parameters best predict effluent total nitrogen concentration, we have to relate all of the parameters that we measure to total N. So we want to ask how well do these parameters correlate with total N, and which ones can serve as indicators for effluent total N. So which constituents should we really focus on that will give us a better idea of how the systems are performing? So to do this, we used multiple linear regression analyses, and we did them, we did separate ones for each system type. So for the Advantex AX20s, there were 2 significant predictors, so the rest were not statistically significant. So ammonium and nitrate were both significant predictors, and they have positive correlations with total N, which means that if they increase, total N will increase as a result. And for the fast systems, there were 3 significant predictors: ammonium nitrate and biological oxygen demand, and these all had positive correlations with total nitrogen. And for the Septic D systems, there were 3 significant predictors as well, so nitrate, pH, and average forward flow, and all 3 had negative correlations with total N. So if they increase, total N will decrease as a result. So as for the average forward flow having a negative correlation with total nitrogen, we think that this is because an increase in average forward flow would dilute the concentration of nitrogen within the system and therefore result in a lower total nitrogen concentration in the effluent. And we're not too sure what's going on with the negative correlation between nitrate and total N, but we're looking into that further. And the relationship between total N and ammonium nitrate and biological oxygen demand is explained by total N being comprised of 3 different nitrogen species. And so if they increase, that would result in an increase in total nitrogen to balance out that equation. So that is explained pretty logically. Also, a decrease in pH would make it likely that the pH would veer outside of that optimal pH range of 6 to 8. And if that happens, the microbes that complete nitrification and denitrification will not be performing as well, and as a result, we would get an increase in total nitrogen. So in conclusion, accurate rapid tests are available. So we identified that 5-in-1 test strip that tests for pH and nitrate, and then that test kit for ammonium. And also we identified that if you use the test strips indoors, it would actually give you reliable results. So that is a possibility as well. And differences in regulatory requirements for monitoring influences management and may affect performance. So we see that increased performance in the Barnstable County systems that receive more operations and maintenance. And ammonium nitrate, BOD, pH, and average forward flow are significant predictors of total nitrogen. So I guess my pictures didn't show up, but I just wanted to let everyone know where we are now in the project. So we're still continuing to collect and analyze the samples, and we have our final sampling event in August. And we're working with the service providers currently to evaluate those underperforming systems and make adjustments to the systems to make them better. And to leave on a hopeful note, we know that the monitored Massachusetts systems are performing a little bit better than our Rhode Island systems, but we know that ours can perform to standard. And also, one town in Rhode Island is considering requiring effluent sampling during O&M visits. So I think that's it.
Thank you, Brittany. I'd like to invite attendees to send me questions via the chat function so that I can ask them to Brittany. We do have one question that came in during the session, and that's, are advanced systems only required for new construction, or are there retrofits required?
That they're required for both. So for critical resource areas, the nitrogen removal systems are required because they're within that critical resource area for nitrogen. But also there are upgrades that are occurring here to old systems.
Thanks. Any other questions? Here's another one. Are there any benefits to phosphorus removal by the advanced nitrogen system?
We have not studied that. I'm not sure. I don't think, because these systems are focused on the coupling of the denitrification and nitrification, I don't think that there would be any benefits of phosphorus removal, but that would definitely be interesting.
Yeah. Any other questions for Brittany or comments? Seeing none, I think we'll wrap this up. Thanks again to everyone who attended and to Brittany for speaking.